Shooting an electron. An electron is projected with an initial speed v0, 1.60 10 to 6 meters per second, into the uniform field between two parallel plates. As shown in the figure, this electron is projected into this uniform field, which points downwards with initial speed v0. Assume that the field between the plates is uniform and directed vertically downward and that the field outside the plates is zero. The electron enters the field at a point midway between the plates. Part A, if the electron just misses the upper plate as it emerges from the field, find the magnitude of the electric field. So it comes out, it just misses the upper plate as it leaves. Now you can see height h is 1 centimeters, width w is 2h or 2 centimeters. That is what is shown in the figure for the geometry of the plates. Okay, so free body diagram of the electron shows that there is the mass of the electron times the gravitational acceleration pointing down. Because the electric field is pointing down, that means we have a positive charge distribution on the upper plate and negative charge distribution in the lower plate, so that the electric field points down. And the electrical force the electron will feel is going to be pointing upward, because it will feel the attraction of the positive charges and repulsion from the negative charges. Or we can say because of the negative charge of the electron, it is in the opposite direction to the electric field. All right. The distance it travels on the y-axis is basically, you can see here, h over 2. So if I write the net force on the y-axis for this electron, it's going to be the electrical force E times E. That's because the weight of the electron, MEG, is much less than the electrical force. So we can neglect this force in this diagram. So this is going to be responsible for the mass of the electron times its acceleration on the y-axis, AY. So we can see that the acceleration on the y-axis is the charge of the electron, the electric field, divided by the mass of the electron. Okay, and therefore we have a constant electric field multiplied by the charge divided by the mass, a constant acceleration. So I recognize this motion as constant acceleration motion of the electron. Now, the distance the electron travels on the x-axis is the width, w, and there is no acceleration on the x-axis. W is equal to 2h, and that is equal to the initial speed v0 multiplied by the time of flight, delta t, the time of the travel in between the plates. Okay, so this delta t is equal to the time spent inside the electric field. So this is the time spent in the electric field. And how much is it? It's going to be the distance it travels, 2h divided by the constant speed on the x-axis, v0, and the distance it travels on the y-axis is delta y. It is 1 over 2 ay delta t squared, because we have a constant acceleration motion starting with 0 y component of the velocity. And the distance it travels on the y-axis is actually half the height, h over 2, which is equal to 1 over 2, the constant acceleration, the electrical force, E times the electric field, E, divided by mass of the electron times delta t squared. Delta t time spent in the electric field is 2h over v0. So the square is 4h squared divided by V0 square. Now you can see that the 2's will cancel, and I will also get rid of one of the H's here. So I will find the electric field to be mass of the electron, initial speed squared, divided by 4 electron charge times h, the distance between the plates. So that's going to be the answer if I substitute the numbers. Now, what is the mass of an electron? Mass of the electron is 9.11 10 to minus 31 kilograms. That's the rest mass of the electron. The speed with which it enters the field is 1.60 10 to 6 meters per second. The electron charge is 1.6 10 to minus 19 coulombs, and h, the distance between the plates, is 1 centimeter, 1 times 10 to minus 2 meters. So if I substitute these numbers, I find the electric field to be, for mass of the electron, I substitute 9.11 10 to minus 31 kilograms. Then I have V0 squared, 1.6 10 to 6 parentheses squared. 4 times the electron charge, 1.6 10 to minus 19 coulombs, times h, 1 10 to minus 2 meters. This gives me an electric field of 364 newtons per coulombs. And now I also want to go back and check the assumption I made about the weight of the electron. The gravitational force is mass of the electron times the gravitational acceleration g. It is 9.11 10 to minus 31 kilograms times 9.8 meter per second square. It is 8.90 10 to minus 30 newtons. If I look at the electrical force, it's the electron charge times the electric field E. It is 1.6 10 to minus 19 coulombs multiplied by the electric field I have calculated, 364. This force is 5.82 times 10 to minus 17 newtons. So I note that indeed the electrical force is much greater than the gravitational force. So my assumption about neglecting Fg is correct. Fg can be neglected in this calculation. The weight of the electron can be neglected in this calculation. All right, so I have an electron that enters a uniform field with an initial speed v0 horizontally, and it travels a distance h over 2 on the y-axis and 2h on the x-axis, and it just misses the upper plate as it comes out of this electric field. Because the electron has negative charge, electric field is pointing down, the electrical force is pointing up. So under the influence of this constant force, E times the electric field, I have a net force, mass of the electron times its acceleration. I have argued that the weight of the electron can be neglected in this calculation. So that constant acceleration is the electrical force E times the electric field E divided by mass of the electron. The distance it travels on the x-axis is 2h or 2 centimeters, which is v0 times delta t, from which I calculate the time spent in the electric field, 2h over v0. The distance traveled on the y-axis is 1/2 ay delta t squared, because I have no initial component of the no initial value of the y component of velocity, and its constant acceleration motion. So h over 2, the distance I travel, is 1 over 2 acceleration, electric field multiplied by electron charge divided by mass, that's the acceleration, multiplied by delta t square, 4h square over v0 square. We find the electric field mv square divided by 4eh. And we can substitute the numbers to find 364 newtons per coulombs. If we calculate explicitly the gravitational force on the electron, mass times gravitational acceleration, it's of the order 10 to minus 30 newtons. The electric force, on the other hand, is of the order 10 to minus 17 newtons. So indeed, the electric force is much greater than the gravitational force, so this can be neglected in this discussion.